I want to show you a little bit just because some people, Excel kind of makes it easier for them to think about things. So the next thing we're going to talk about is combine two different principles. So first, where do I want to go? Here it is. We can do the exact same thing we were doing for means, population means, for population proportions, right? It's going to be a little bit different, right? But we have the same types of tests, right? Greater than or right tail test, less than or left tail test, or this not equal to or two tailed test. Same principles apply. We're just looking at a different statistic here, the proportion instead of the mean. Right? So the steps are going to be exactly the same. It's just that when we turn proportions into z-values, remember the equation was a little bit different. So with our confidence intervals, we said what? With our confidence intervals, when we wanted to find the standard deviation of my sample proportions, we said it should be equal to this, but we don't know what the population proportion was, so we had to use like our best estimate, which was to use the sample proportion. So this is what we did when we were looking at confidence intervals. Well, to calculate a test statistic, we think about the z statistic for a sample proportion. We're going to take, just like before, we took what? Our sample mean minus our sample proportion, our sample mean minus the assumed true mean. So take our sample proportion minus the assumed true proportion. And then what do we divide by? Well, here we had to divide by the standard deviation of our sample means. Now we're going to be dividing by the standard deviation of our sample proportions, right? We're dealing with a different statistic. Now, instead of using the standard deviation for our sample proportions that we were for confidence intervals, well, here we don't, we were estimating the population proportion here. Well, now we don't need to estimate it because we've assumed it's a certain value. So now our test statistic equation, when we're thinking about the standard deviation of our sample proportions down here, we use that assumed true population proportion to calculate that standard deviation for our sample proportions. So here we'll use that assumed true proportion. But once we have this test statistic equation, all the steps are exactly the same for hypothesis testing as they were when we were looking at population means and sample means. Okay. So that's the first thing, right? Was we have a slightly different test statistic when we're dealing with proportions. Now, I mentioned last class, there's the p-value, but there's also the critical value approach. So I'm going to work through some sample proportion examples. We'll probably not get too far into today, but on Wednesday. And I'm going to use the critical value approach with those. However, I can use the p-value approach with proportions. I could use the critical value approach with means. It doesn't matter, right? I'm just going to use kind of proportion examples to show you the critical value approach. And I'll try to make the connection between the p-value and the critical value approach as well, because they're very similar, okay? So, what are we doing with critical values, okay? So critical values are going to be kind of threshold values that we set where we say, look, if I see a test statistic that's more extreme than the critical value I set, I know that I can reject the null hypothesis. Okay? So the critical value is going to be this value set such that if you see a test statistic that's more extreme or larger in absolute value than that test statistic, you know that you can reject the null. And if it's not, you know you fail to reject. Okay? So, this is going to be a little different for left or right or two-tailed tests, so I'll kind of go over that a little bit. But I want to try to make the connection between the p-value and the critical value approach as well. So, what were we doing before? I think the green one shows up a little better here. So we're going to be able to, we're dealing with sample proportions now. So what a critical value is going to be, and let's do a left-tailed test first. The critical value is going to be that z-value that would correspond to a certain sample proportion that the probability of seeing something past this point is going to be whatever you set your type 1 errors at. So my critical value is going to be the z-value that gives me my type 1 error in the tail, okay? So if I had an alpha of 0.05, how could I find that z value? Well, I'm going to work in an inverse, right, or in reverse. I know the area I want in the tail is 0.05. Actually, let's do an easier one because this one I can remember easily. So 0.025. If I look that area up in the middle of my standard normal table, I'll find that the z-score that gives me that area is negative 1.96. Now, for a left-tailed test, because we're using these small alpha values, we know our critical value should always be negative, right? Because, if I want anything less than 0.5, right, my critical value would have to be negative, because 0.5 would be the area to the left of that mean of 0. So my critical value is the z value that corresponds to having alpha in that tail. So essentially, when I find that critical value, I can think about my rejection region is going to be if I find a test statistic anywhere in this range. So, let's say I see this as my sample proportion and I turn it into a test statistic. I know that test statistic, if it falls in this range, I'm going to be able to reject the null hypothesis at it. Well, why do I know that? Well, because if I look at that standard normal table, anytime I see a test statistic that's more extreme than negative 1.96, that just starts giving me an area in the tail that's smaller and smaller than 0.025, right? So I can set this threshold z value and say, if I see a test statistic that's any more extreme, right, or here, kind of a larger negative value than negative 1.96, all those test statistics, let's say I had a test statistic right here, I know that the p-value associated with that test statistic is going to have to be smaller than alpha, right? So it's really just like comparing different sides of the coin here. When I was using the p-value approach, I was comparing the areas in the tail, alpha and my p-value. When I use the critical value approach, well, really what I'm doing there is I'm saying, is that test statistic in the rejection region? I'm saying, is that test statistic in absolute value, is it less than the absolute value of that critical value, right? I'm comparing the z values instead of the areas in the tail that correspond to those z values. So either way is okay. Another way to kind of think about these critical values is it's saying, well, look, I know that if I see anything that's more than 1.96 standard deviations below that assumed true value, then the probability of that occurring is going to be less than 0.025. Because if it was 1.96 standard deviations below, I know the probability of seeing something that's exactly 1.96 standard deviations below the mean is 0.025. So if I see something that's any further away, right, any larger number of standard deviations below, it's just going to be less and less likely I see something that far away, that more than negative 1.96 standard deviations away from that assumed true mean. So we're really just kind of comparing the area in the tail for the p-value approach, and then like the x-axis values, right, the z values when we do our critical value approach. And when I write absolute value here, it's essentially ignoring the negative sign, because when we're dealing with negative values, being greater than is actually being a smaller negative value. So we take the absolute value to make it a little bit easier to kind of think about that. Okay. Any questions on that? Do one more thing before we get out of here, and we'll deal with a tougher one on Wednesday. So what if I was dealing with a right tail test? Well, everything's really going to work the exact same. I'm going to be thinking about, for a right tail test, only evidence on the right goes against the null. So I'm going to set the critical value that gives me alpha in the right tail, right? Let's say we do alpha of 0.025. What's the area going to be in the what's the critical value going to be that would give us 0.025 in the upper right tail? Well, it's going to be the exact same value as the critical value for a left tail test, but we're doing with the right side of the distribution, so positive 1.96. Right? So our left and our right tail critical values will be exactly the same. It's just for a right tail test, they're going to be positive. For a left tail test, they're going to be negative. But then it's the same approach. If I see a test statistic here, we can think about anything more extreme than my critical value is now to the right. So if I see a test statistic in this region that's in the rejection region, I can reject. If it's not in the rejection region, like it's somewhere out here, well, now I fail to reject. And once again, this test statistic, the area to the right of that would be the p-value. Right? So any test statistic I see past this point is going to be giving me an area smaller than 0.025. And if I only reject when the p-value is less than alpha, I'll reject. So any test statistic that's larger than my critical value, I can reject. And here, you know, now when I take the absolute value, it doesn't change anything because they were already positive. But here it's that, okay, if my test statistic, right, is greater than, actually, sorry, I think I had this backwards here, didn't I? If my test statistic is greater than my critical value, I reject. If my test statistic is greater than my critical value, I reject, right? Or more extreme than my critical value. Okay. Any questions on that? I went a little bit over here, so I got to let you guys out. But I'll probably put up, I'm going to put up an online quiz when I get back to my office this afternoon. There'll probably be a problem that gets you kind of an example that you can start to work through one of these on your own. And then maybe just a couple general questions, more so for me to get an idea about where everyone's understanding is at and kind of how to proceed for Wednesday and Friday. Okay? All right. I will see you guys on Wednesday. Okay. So, as I mentioned last class, the exam's coming up next Monday, Tuesday. Should look kind of similar to the last one, probably 2 short answer, 10 to kind of 12, somewhere around there, multiple choice. I'm still kind of finalizing it. I'll have kind of the exact breakdown of the questions on Friday, but for now, let's kind of jump back in and make sure we can kind of get through some hypothesis testing, which is what we've been talking about. We left off last class. Oh, we don't need all this. So we're starting to talk about critical values and kind of how we can work through some population proportion examples using the critical value approach as opposed to the p-value approach. So I kind of made the connection between the p-value and the critical value approach last class, but we'll kind of start out a little bit of a reminder of what we're doing. There we go. So what we're doing with critical values is we're saying, okay, I want to figure out what the z-value is that's going to give me this kind of threshold, this cutoff alpha in the tail, right? If I see a test statistic that's anywhere kind of in this range, right, more extreme than my critical value, so let's say my test statistic ends up being right here, then I can reject, because really what my critical value is, let's say we wanted an alpha of 0.1. So I go to the standard normal table, I look up that area in the tail of 0.1. What I'll find is, I believe, negative 1.29 is the z-score that would give me that desired alpha in the tail. So alpha was this kind of proportion of type 1 errors that we were making. That's what we set. So if I see a sample mean that's any more than 1.2 standard deviations below the assumed true mean, right, that's what that kind of critical value is going to represent. It's still a z-value. So I could map it back out, and actually we're going to be doing proportion examples today. So we're going to have some assumed true proportion, population proportion. If I see any sample proportion that's more than 1.29 standard deviations away from that assumed true value, then I know I can reject, right? Remember, my test statistic and my critical values are still z-values. So they still represent the number of standard deviations away from this assumed true population proportion, or the assumed true population mean, right, depending on the example we have. So, you know, if I see a test statistic out here, I'm going to fail to reject, right? It's not kind of in that rejection region. It's actually less than 1.29 standard deviations away from that assumed true value. Okay. So we said, you know, one way we can always kind of remember if the test statistic is more extreme, or if we take the absolute value of the test statistic, it will be larger than the absolute value of my critical value. And the reason why we have to kind of ignore that negative sign is right because here, a test statistic that's like more extreme than my critical value would actually be a larger negative value, so it would actually be less. So it just makes it easier if we just think about the absolute value. Right? That way, we're just kind of comparing the size of my test statistic and critical value. To kind of relate this to the p-value approach, remember, anytime I see a test statistic over here, that p-value is the area in that tail. Notice, whenever I have a test statistic that's more extreme than my critical value, that area in the tail, that p-value would be less than alpha, which is another way we said we can make the rejection decision, right, using the p-value approach. So both things will lead to the same decision, just we're comparing the area in the tail versus kind of the x-axis value. Okay. So that's kind of where we left off. We said that these critical values for a left tail test, right, would all be negative. You can kind of think about what would the critical value be if I had an alpha of 0.5. So the area to the left here, if it was 0.5, well, that would be whatever the mean of my standard normal distribution is, which is 0. So you can see that for a left-tailed test, when I want little, small areas in that tail, 0.1, 0.05, 0.01, all those are going to be an area less than 0.5. All my critical values will be, negative. If I had a right-tailed test, and I wanted an alpha of 0.1 in my upper right tail, well, the area to the left would be like 0.9, 0.95, and 0.99. So all my critical values for a right tail test would be positive. So we kind of had the same values for left and right tail test, but positive and negative. And then for a two tail test, we said we had pairs of, let the screen catch up here. So for left and right tail test, we get the same values, but for right tail test, positive critical values, left tail test, negative. For a two-tailed test, we'll have kind of pairs of critical values, and that was because alpha was the total area in the tail, right? But when we have two tails, it's the total area in the tails. So what we were doing there was saying, okay, what critical values now would give me kind of alpha over 2 in each tail, right? So there we're going to have two critical values because evidence on either side could go against the null. Okay, any questions on that before we kind of keep moving into an example? Probably make a little more sense once we start working through it. So we have our test statistical equation that we're using before, but we said, for a proportion example, it's going to look a little bit different. So kind of putting all this together, we have like a nice synopsis of kind of critical values, left-tailed, right-tailed, two-tailed. Steps are going to kind of be very similar to what we're doing with the sample mean. It's just now with the critical value approach, instead of using our test statistic to find the p-value, we'll use alpha to find the critical value, right? And then compare the critical value to the test statistic. So let's just work through an example. I think that will help. So I'm going to show you kind of something unique with this example as well, to point out, to kind of make a point, I should say. So we've got this question. We want to test for whether or not the true population proportion of people who own guns is not more, or sorry, whether or not more than 50% of people own a gun. So that's what we want to test for. So our alternative hypothesis is that this true population proportion is greater than 0.5. So we assume the opposite is true, which is that it's less than or equal to 0.5, right? Or 50%, as a proportion is 0.5. We take we look at a recent poll of 100 people, so we've got n is equal to 100, and we find a sample proportion of 0.41. Okay. So right away, first step, identify the null and alternative, right? Should be B here, right? But the null is that it's less than or equal to 0.5. Now I can go through and start to find things like critical values and then test statistics, but if I look at this, what's going to be the rejection decision here before I even kind of, I can actually make the decision without working through this one. If I look at my sample proportion, does it go against my null? No, 0.41 is in fact less than or equal to 0.5. So I actually found evidence that supports the null here. So of course I'm not going to reject it. But even if we work through it and use this critical value approach, you'll see why we would fail to reject. So first of all, let's try to find these critical values, right? Well, what type of tailed test do I have? I have a greater than sign in my alternative hypothesis, so I have a greater than or a right-tailed test. So automatically, I know that these critical values should be positive, right? I'm looking at the right side of that distribution, so I can rule B and D out right away. So now I'm between A and C. Okay? So how can I figure this out? Well, what I want to do is think about, for that, let's say we'll do the alpha of 0.1 first. So if I wanted the critical value, that gives me 0.1 in this tail, right? What I can do, oops, sorry, I can actually write that. What I'll do is, oh, we already kind of jumped the gun here, but I'll go to that standard normal table. What I could do is hunt down 0.1. So start scrolling. Looks like it's somewhere in between these two values. So negative 1.28 and negative 1.29, I was in between. So I'll use the larger of the two. Now here I found negative 1.29. That's not my critical value. I already know my critical values need to be positive. Well, that's because I'm dealing with a right-tailed test. When I look up the area to the left, I was looking at 0.1. Well, that would actually mean that the area to the left over here is 0.1, and I wanted the area to the right to be 0.1. So I could do two things. I could know that this is a symmetric distribution. So the area to the left of negative 1.29 is 0.1. The area to the right of positive 1.29 should also be 0.1. Or I could have said, well, I know if I want the area to the right to be 0.1, the area to the left would be 0.9. If I had looked up 0.9 in my table, let's keep scrolling down here. I'm getting close. In between these two, 1.28 and 1.29, sure enough, I'll find that same thing. So you can either, for a right-tailed test, you're going to have to kind of think about what the area to the left is and look up 0.9 instead of that alpha you want in the upper right tail, which is 0.1. Or you can remember it's a symmetric distribution, and if I just look up alpha of 0.1, I'll find the value I need, but for a right-tailed test, it should be positive. Okay? The other way I could do this is kind of using my student t-tables. Remember something I said about those. This last row would be the values that you find from a standard normal distribution. So actually, it's kind of nice if we use the student t-table to kind of cheat a little bit, I guess. 0.1, 0.05, and 0.01 were the areas I wanted in that upper right tail. 1.282, 1.645, and 2.326. So that's kind of accurate out to the third decimal. If I had looked them up in the Z table, I could do that one by one. What I'll actually find is I have to round into the second decimal, and so the critical value for 0.05 is 1.65, and then the critical value for 0.01, 2.33. So I can think about wherever my critical value is, the area to the right, that's kind of my rejection region. So if I want to remember, here I've got kind of the 10, 5, and 1% significance levels. So which of these levels can I reject the null at? Well, it depends on where my test statistic is. So to find my test statistic, let's see if this shows up a little better. So we've got, our equation was take that sample proportion, subtract the assumed true proportion, and here we're going to divide by the standard deviation of my sample proportions, which we can calculate using the following equation. All right. So from here, it's a matter of plugging our values in, right? The sample proportion we found was 0.41. That assumed true proportion comes from the null hypothesis, is 0.5 divided by square root of 0.5 times 1 minus 0.5 divided by our sample size of 100. Right. if we do that, notice we saw something below the assumed true proportion, so we'll end up with this negative 1.8 test statistic. Okay, so this is my test, or my Z statistic. Well, clearly, my test statistic is nowhere near my rejection regions, right? I mean, it's not even the right sign, right? So this is an interesting, this is a not interesting one in that we clearly failed to reject at all these levels. We're nowhere close to being in that rejection region. Any questions on that before we keep moving? So what would have been more interesting is if I had seen something like, let's assume I saw a test statistic of 1.8. Right? That might be a little more interesting. Because a test statistic of 1.8 would mean I can reject at the 10% level, because I'm in that rejection region. I can reject at the 5% level, because I'm in that rejection region. But I couldn't reject at the 1% significance level because I'm not quite that far out, right? I was 1.8 standard deviations away from the assumed true value, assumed true population proportion. And that 1% level, I needed to be at least 2.33 standard deviations away. Any questions over that? Okay. So we found those three critical values, we plotted them. I think a lot of times with the critical value approach, the visual really helps, right? It's kind of easy to see if I draw the rejection region out. We calculated our test statistic here, kind of using our proportion test statistic equation, right? And we actually could find the p-value as well. So here I'll kind of show you why using two approaches you get the same answer. So this is kind of a weird one because the evidence actually supported the null. But if I wanted the p-value, right? Well, for a right-tailed test, it's still going to be the area to the right of my test statistic. So it's going to be the entire area to the right here would represent my p-value. Or if it kind of helps to see it a little bit cleaner, what we're thinking about is we found a test statistic of negative 1.8. The area to the right represents our p-value. Well, I can look this value up on my standard normal table. Not the t table, I want the z table. So I had what, negative 1.8, 0. So remember that 0 is that first column. So negative 1.8, 0.0359. But that's the area to the left. I'll need to subtract that from 1 to get the area to the right. So what is this, 0.9641? Okay. Now, with a p-value of 0.96, what levels can I reject at? Well, remember, for the p-value approach, we reject if the p-value is less than alpha. Well, typically the alphas that I look at are 0.1, 0.05, and 0.01. If I have an alpha of 0.96, that's not going to be less than any of these, right? So here, I'd fail to reject because it's not less than any of the alphas. I only reject if the p-value is less than alpha. And so both those approaches line up. The p-value approach, I clearly failed to reject. I'm nowhere close to being able to reject. Critical value approach, same kind of thing. I'm nowhere close to those rejection regions. So they would both lead to the same decision. Any questions on that before we keep moving? All right. So we kind of already talked about we don't reject at any of these levels, right? And yeah, I like this meme at one time. So test statistic in the rejection region, null hypothesis, not in my house, right? So we don't reject at any of these levels. Okay? So let's look at maybe a little bit more interesting of an example where we don't have evidence that supports the null. So let's say you want to test against that well, that shouldn't be repeated twice, that less than 15% of Indiana mothers smoke while pregnant. So I haven't worked through an example like this, and typically when it comes to the exam, I will tell you, right, whatever you're testing for. So that's how I've worked through all the problems up to this point, where whatever you're testing for, that's your alternative hypothesis. You then assume the opposite is true. Another thing that we kind of use terminology-wise is whatever we're going to test against is actually our null hypothesis. I don't want to kind of trip you up, though, so on the exam, you won't see something phrased this way, right? But I want to start to introduce it because we will start working with problems after the exam with hypothesis testing, just slightly different, where we might start to be told what we're going to test against. So if we're told what we're going to test against, that becomes our null hypothesis. Okay. So here, I've got that I want to test against it being less than 15%. Oops, I'm getting stuck there. So our null will now be that the population proportion is less than 0.15, and the alternative hypothesis is that it's greater than or equal to 0.15. Or, sorry, we could do that, but I've already told you we always keep the equality on the null, right? So this is just that it's greater than 0.15. So I've got a greater than sign in the alternative hypothesis. So I've got a greater than or a right-tailed test here. The sample proportion I found was what? 0.18, and it was 72 people. Oh wait, sorry, 72 out of 400. So my sample size is 400 there. Now this is one also where I did tell you what the sample proportion was, but if I didn't explicitly tell you it was 0.18, another way you could have calculated this was, well, it was 72 out of 400, and that's how you would find that sample proportion of 0.18. Okay? So I could expect you to do something like that in the exam, right? Where I tell you instead of, maybe I take this part out. Well, what's my sample proportion? Well, it's just 72 out of 400, which works out to be 0.18. Okay? Here I was nice, and I kind of put it in here. Sometimes I'll do that in some questions I won't. Just depends on kind of changing the difficulty level of different problems. Okay? So we've got our null and alternative hypothesis. We said we have a right-tailed test. What are our critical values going to be? Well, actually, I should know very quickly what these critical values are. Right? Because if I'm doing a right-tailed test, and I want the areas of 0.1, 0.05, and 0.01, well, those are going to be the same three critical values. Let's see if I can find it, that I found before. It's not going to change. I'm still looking at the standard normal distribution. So when I go to look up those alpha values in the upper right tail, I'm going to find those same three values of 1.29, 1.65, and 2.33. Here's my rejection regions at each one of those levels. Okay? So right away, if I have a right-tailed test, what are my critical values going to be? It's going to either be A or C again. Sure enough, it's the exact same three. I can look them up, but I'm looking them up in the same table every single time, so it's always going to tell me the same three Z values. Okay? Any questions up to this point? What if I had a left-tailed test here? What would the critical values be? Yeah, same three values, but now I want those areas of alpha in the left tail, so it'd be the same three values, but negative. Okay. So the next step is let's calculate our test statistic. So if you look in the kind of exam 2 practice file folder, there's a formula sheet. So it's got all the kind of formulas laid out. We'll probably take a look at that at the end of class on Friday. We'll start doing a little bit of review at the end of class on Friday. But it's going to show you this equation. It leaves this part off, but just as it it leaves this part off, right? The standard deviation of my sample proportions, but it just puts it right into the formula for you. So you'll see this, and the whole thing is getting taken the square root of. So I found a sample proportion of 0.18. The assumed true proportion was 0.15. So it's just a matter of plugging things in at this point and making sure that you use that 0.15. Okay. So I'm not sure what it is off the top of my head, but if we go to compute this test statistic, right, let's see what it ends up being. Plug everything in. We get about 1.68. Right? So notice my test statistic is, I was only 0.03 away from that assumed true value. So you might think, oh, this is going to be like a test statistic of almost 0, right? We're hardly any distance away from that assumed true population proportion. But that standard deviation of my sample proportions is really, really small. So even being 0.03 away was, more than, more than 1.5 standard deviations. So I've got my test statistic. The next step is I basically just plot it. Where would it fall? It would just be right on the other side of that critical value. So 1.68 is just right above 1.65. So I can say that I would reject at the, 10% and 5% levels, right? But I would fail to reject at the 1% level, right? Because I'm not in that rejection region. Okay? Any questions on that one? I think I've got one more that's a two-tailed example. So where are we at on time here? Oh, we got